Hey everyone, welcome to the 11th week of the Chromatic Notes Consult seminar. Today's speaker is Rushil from Harvard, and Rushil will be talking about construction of E-theory and power operations on E-theory. So, yeah, Rushil, please take it away.
Okay, sounds great. Thanks for having me. Yeah, so what this is going to look like is that we're going to start with doing just a quick review of Murabba E-theory, to sort of talk about like where it comes from. Uh, Next, I'm going to define the notion of a power operation and give some examples of why these are, very useful things that we see a lot of the time in topology. And then finally, I'll say something about power operations in E theory, which, to sort of cut to the chase, is really nice because we have like a very concrete sort of algebraic description of what power operations on like algebras over Morava E theory really look like, and we can use this to like prove lots of useful things. So I won't really like tell you what this algebra is because it's like kind of disgusting and like you can like look it up, but I will like sort of prove a nice lemma that comes up in the study of these things that has like a lot of like really cool practical applications. Okay, so let's get started. Um, First, okay, so for the rest of time immemorial, let's fix a prime p and some finite height. And now, what we want to do, or where Morava E theory really comes from, is that we want to understand the formal neighborhood of the locally closed substack of the moduli of formal groups of at prime localized at P and at height like exactly n. And it turns out that this is related to, in some sense, deformations of height n formal groups. So how are you going to set this up? Um, so let K be a perfect field So you can do this in general with like any perfect FP algebra, but for us, we're going to really want this to be a field. Um, Characteristic P, and we're going to let gamma naught, or equivalently F naught, be a formal group, or its corresponding formal group law um, of height n over K. Um, just brief reminder that if you're working over a local ring, so in our case a field, like that's fine, um, like every formal group is coordinatizable. You can always like represent it as coming from a formal group law. So like we don't lose too much in like going between these two notions. Okay. So we want to study like deformations of these formal groups. So to do that, we need to introduce the notion of an infinitesimal thickening. So definition, an infinitesimal thickening of K is a surjection, right, phi from some algebra, some ring A to K with some maximal ideal given by the kernel of phi such that A is an Artinian local ring. So this can be phrased in terms of some like descending chain condition, but what this means sort of concretely is that first, if I take powers of this ideal, this has to vanish for A sufficiently large. And secondly, is that the successive quotients are finite dimensional K vector spaces. You might ask, okay, so like why are these things not the same thing as Artinian local rings with residue field K? Well, they are. The point is that to talk about the notion of infinitesimal thickening, you really want to sort of capture the notion of like this surjection here. Like that's part of the data. Okay, so associated to that, a deformation of, for now we'll do this in the formal groups version, formal group law version of F naught to A is a formal group law F over A such that the push forward of F is F naught. Equivalently, if you write this in terms of the corresponding formal groups, what you get is that, so you start with some formal group G naught, or I guess I call this gamma naught, over spec K, and then the data of a deformation of an infinitesimal thickening of K is the same thing as a map from spec K to spec A. So you think of like including K as like the close point of some formal neighborhood around it. That's like what a local ring is. And then what you want is a formal group gamma over spec A such that this is a pullback diagram. So let me do this in a different color. So then you might ask, well, it's a fact, and this is like sort of where we're using that we're working over like a perfect field. But def A, so this is formal groups or equivalently formal group laws over some deformation or some thickening A lifting F naught. So this thing is naturally a discrete groupoid. What that means is that you can define what a morphism of deformations is. It's the thing you expect. Like a morphism of deformations over A, it's the thing you expect. And it turns out that like uh, any isomorphism of deformations is actually like the identity. So there's like, so even though this is like naturally a groupoid, you can really just identify this with a set. And what that tells you is that you get a functor from art K of thickenings of K to sets given by taking the set of deformations. This is all associated to that like fixed formal group we chose at the beginning. So then the question is that, okay, so can you understand this functor? And this is basically the subject of this thing called Lubin-Tate theory. So I'll just tell you the answer. It's kind of long. So first, let WK be the ring of p-typical Witt vectors. Now, if you haven't seen this before, what this is it's a construction that sort of generalizes how you get the p-adics from FP. And it's characterized by the following two properties. So first is that this thing mod P will just recover K. And two is that WK is ZP flat and p-adically complete. Okay. So now let R be WK, and then we're going to take a power series ring on variables V1 up through Vn minus 1. where n here is just the height. And we know that by this property A up here, this thing has a natural surjection down to K, and then the kernel of this thing, which we're going to call this maximal ideal M, is just the ideal generated by P, and then all these elements V1 up through Vn minus 1. Three. So if you recall our formal group law F naught, we can think of this as a map from the P localized Lazard ring to K, where this thing, if you remember, is just Z localized to P, and then it's polynomial on some generators. And because F naught is height n, what that implies is that this map, which I'll call, say, phi naught of t to the pi minus 1 is equal to 0 for I between 0, 1, and minus 1. So what we can do is just pick any lift phi of phi naught from L localized at P to R, such that now phi will send Tpi minus 1 to Vi, again for 0 less than I less than n. So what that gives us is that this gives us a new formal group law, F, over R, which is like, and this satisfies a property, of course, that if we call this surjection, this thickening, I don't know, let's call it psi, then psi pull or psi push F is just equal to F naught. So it's great. And it turns out that this explicitly constructed formal group law we have here is in some sense the universal formal group law. It's the universal deformation of F. So what this theorem is, and this is due to Lubin and Tate, is that so the formal group law F over R is the universal, sorry, is the universal deformation of F naught, in the sense that have the following equivalence of functors, or the natural isomorphism from morphisms between infinitesimal thickenings of K to deformations over such any given thickening, where here we send a homomorphism R to A to the push forward of this universal deformation. So that's cool. If you want to describe this in a way that's like more formal group theoretic, what we can say is that there exists a formal group law G, or let me call this gamma, over spec R, which is the universal deformation of gamma naught over spec K. Where, like, remember, this R is like a massive, massive ring. Okay, that's great. And then here's the useful fact that you need, is that F over R is Landweber exact. And I believe we talked about what this means already, but just to briefly recap, it means that the regular sequence the sequence P V1 all the way up to Vn, Vn minus 1 is a regular sequence. And this is basically sort of like by construction. And Vn is invertible. in R mod this maximal ideal M, which remember is just our original field K, and that's because the formal group law we started with had height n. Okay. So by the Landweber exact functor theorem, we get an even periodic ring spectrum, which I'll call En, such that homotopy groups of this thing are Wk, then a power series on V1 to Vn minus 1, and then we have an invertible generator where this thing lives in degree 2. And then this thing is usually called Morava E theory. I want to emphasize that like this construction really depends on the choice of perfect field and formal group. But it doesn't depend too much on it. Like it turns out that like any two choices of formal group of height n are like sort of isomorphic, at least over some like algebraic closure. This is Lazard's theorem that sort of like geometric point that like for a fixed prime and height, like there's exactly one geometric point in MFG. Um, and And what this implies is that like localization with respect to Morava E theory, which is often called like just N localization, is like a well-defined thing. And it turns out that this actually agrees with something that people knew about a long time ago, which is Johnson-Wilson theory, which confusingly is also often referred to as E theory. I think is like terrible abuse of notation, um, which comes much more cleanly out of like you take like the Brown-Peterson spectrum and you like invert some elements and then kill off the rest of them. It's like some very much older construction. Um, and in fact, there's like a cool geometric picture that you can associate to like EN localization. So if you consider, um, so maybe let's consider for a fixed prime, we have the moduli stack of formal groups localized at P. So here, this is like height 0, this is height 1, 2, then all the way up to height n, and then, this just keeps going on. And what EN localization does is we just restrict to the open substack of height less than or equal to n. So we're just restricting to MFG less than or equal to n contained in MFG. So this is just something that's like relatively straightforward to show. It turns out that doing the opposite thing, which is restricting to the closed substack of height exactly equal to n inside MFG less than or equal to n. So like this localization is much harder. It turns out that this thing is exactly a Kn localization, which is like kind of nice. You imagine that like Kn is like this point, and then En is like this collection of points. But yeah, so that's sort of the general picture. And then I guess the other really useful fact about Morava E theory, this is due to Goers, Hopkins, Miller, is that En has a unique, or essentially unique, E infinity structure. So it's like this very like highly commutative, highly coherent object. And if you take gamma naught to, if you take K to be FPN and gamma naught to be the Honda formal group law of height n, these are like just like explicitly nice choices of like some perfect field in an associated formal group, um, then the big Morava stabilizer group, which you can write as the little Morava stabilizer group, a semi-direct product, the Galois group, Fpn over Fp, where this thing is just the sort of automorphism group of the pair Fpn gamma naught. So this thing will act on En by E infinity maps. So what you eventually see is that you have this like really cool picture where so you have like Morava E theory, you have a sort of reduction map to K theory, Morava K theory, which is like taking the residue field. And then you can actually construct E theory as a sort of pro-Galois extension of the K local sphere, where you can first sort of take just the sort of pro-Galois extension of the little Morava stabilizer group to this thing, and then just take the, sorry, so this thing is just the sort of Galois extension against this factor, and then here you just take the extension to Sen. And what this lets you do is that you can then recover the Kan local sphere spectrum as the homotopy fixed points of the action of the Morava stabilizer group on Morava E theory. And like this thing is like incredibly powerful. So this gives you this thing called the descent, or this gives you a descent spectral sequence, which lets you like compute like really concrete things about this object, which is like super useful via like continuous group cohomology. So I won't say too much about that. That's like a very well explained subject. I think a good place to read about this is probably like what's it called? If you check like the Handbook of Homotopy Theory, there's like some article in there. This is like a good place to learn this stuff. Yeah. Um, who's it by? It's yeah, so this is Tobias Bartel and Agnes Beaudry, the Chromatic Structures and Stable Homotopy Theory. It's a great paper. You should totally read it. Okay, so great, that's Morava E theory. So now I'm going to sort of pivot away from that for a bit and tell you about power operations. But before that, are there any questions so far? Okay, so let's continue on. Now, the key idea with power operations is that ring spectra, okay, how should I say this? So the idea of power operations is that if I give you the sort of like cohomology taken with respect to some like commutative ring spectrum, then like being commutative as a ring spectrum, or like being commutative as a ring is like just a very strict condition, right? Just like, you just like write it down. But like for ring spectra, this is like a much more like, you should take into account a lot of coherency data, which tells you that like taking like products on cohomology classes is like commutative, but it's not like too commutative. There's like sort of higher order like corrections that show up. So one way to set this up is that, so here's like a very extended example. So say that R is a commutative ring spectrum. So every commutative ring spectrum gives you a multiplicative cohomology theory. The converse is like not precisely true. Like you need this to be like a very what's it called? you need it to be like a particularly nice um, multiplicative cohomology theory for it to like to know that it like sort of refines to an E infinity structure on the ring spectrum you started with, but like whatever. So let's say you have a commutative ring spectrum, and then you have some element in the R cohomology of some space slash spectrum X. And then what you want to ask is that like, okay, so like what is the cup product on X? Well, it's the following thing. I take a pair of cohomology classes, which is the same thing as a pair of maps from X cross X to R cross R. Then on R cross R, I have a map, which is like product, which is like, and then this composition is the cup product of these two cohomology classes. Or like maybe I'd like need to like include um I'll like include this by the diagonal, and like that's like the cup product of two cohomology classes. Like this thing would be like this thing is for like the cross product of cohomology classes. Um Now the cup product is like commutative, but it's not like too commutative. So what the issue is that let's say I take um I take the n-fold power of a certain element. So let's say I have x to the n mapping to r to the n via the element that's like sort of justifiably called a to the n. Now, I want this thing to factor through the quotient by the symmetric group that comes from like exchanging all these factors. But it turns out that, like this thing isn't like sort of true on the nose because this multiplication isn't like actually commutative. It's like an E infinity structure. So what this means is that what I really should be doing is instead consider the sort of extended power construction where instead of taking like this thing naively, I write down something like uh okay, so like I guess I need to fix some E infinity operad that's just going to be like sitting around. So maybe what I actually need to write is something like this, where like here, the fact that I can quotient out by the symmetric group on this thing is a reflection of the fact that like this cup product, like that's like how this E infinity structure sort of comes to you. And then you can call this whole composite something like the pth or the nth sort of power of your class alpha. Now, if you restrict along the diagonal copy x in xn, so like because this is something that you could really do uh, for like any sort of n tuple of elements in X. Now, if I restrict along this diagonal copy, what do I get? Well, then I'll get a map from O(n) mod sigma n to X all the way to R. So I have a map like this, which is equivalently a class in the R cohomology of B sigma n times X. And this thing is usually called the total nth power operation of alpha. So here's a concrete example of that. So let R be the mod 2 Eilenberg-MacLane spectrum, let n equal 2. So quick, just show of hands to see who's listening. Um, if I take the classifying space of the symmetric group on two elements, this is just the classifying space of the cyclic group on two elements. What is this? This thing is RP infinity. That's great. And now what that tells me is that this sort of power operation construction like square operation construction gives me a map from the Mallarapu cohomology of X to the Mallarapu cohomology of X cross RP infinity, which is isomorphic to the cohomology of X mod 2 on a single polynomial generator, which I'll call T. And this thing you already know, this is just the sort of like total Steenrod operation. So explicitly, this sends a class alpha to the formal sum square I alpha T to the I. So there's a couple sort of general things that you should get from this picture. One is that these power operations are things that you can like sort of construct very concretely. But also that to get an operation that's like, so like here we go from like cohomology of X to the cohomology of like X cross some other thing. If we want to get something that's like actually in the cohomology of X again, we need to somehow like kill off, or like we need to like sort of project onto one of these factors. In general, this means we need to pick an element in the R homology of this classifying space and like just pair with that so we can get something back in X. So we'll see this principle sort of appear later on. But I guess sort of the general claim here is that these power operations are both like really useful, and then like in the case where you know like even little bits about how they relate to each other, you can like get really useful obstructions. And like this is like sort of the general pattern. A lot of algebraic topologies want to like come with like powerful obstructions to things like not happening. So let me give an example, a sort of toy example that's sort of using this theory of Steenrod operation. I think is like very, very well known. This goes back to like the 1970s. And it's the following question. So I can consider the following thing. So let's take, so this is a diagram in spectra. I can take the multiplication by 2 map on the sphere spectrum and take the cofiber of this, and this gives me something called the mod 2 Moore spectrum. Maybe you want to think of this as like the suspension spectrum of like RP1, or probably RP2 or RP infinity, something like that. And then the cofiber of this thing is of course just the suspension of the sphere spectrum. Now you can ask, because you know, okay, so like the sphere spectrum is a ring spectrum, like obviously it's like the initial ring spectrum. And you can ask, okay, so does M, the mod 2 Moore spectrum, have a multiplication? So let's think about this for a second. What does this mean? So we'd have some map. So let's say it does. So we have some map M cross M to M. And then one of the actions of being a multiplication is that this has to split the identity map. And what this means is that if we take this exact sequence and we tensor it up by M, I guess we'd have. So this map here would be like 1 times the unit map, because we know that like this map here is just like sort of definitionally the unit map on M, or like a sort of a candidate for a unit map. So a multiplication would actually split this. And check that. And that would imply that M smash M would be equivalent to M wedge suspension M. And it turns out that like this thing is true additively, or like So you can ask, okay, so like, is this true? If you compute cohomology, you get that these things are like the same cohomology additively, but they differ in their Steenrod operations. So this is like the abstraction here. So let me explain what I mean. So recall, this will be really brief. So I have a family of operations, square n, on the cohomology of some space / spectrum X. What this looks like is that, let's say I have hm of X, then I have operations going to hm of X to hm plus 1 of X, all the way up to h2m of X, where this top operation is square m, and then this thing just corresponds to taking the literal square. This first operation is the Bochstein homomorphism. And here, okay, I guess we're just saying that so this is with F2 coefficients, where this Bochstein is the thing that corresponds to the coefficient sequence 0 to F2 to Z mod 4 to F2 to 0. And then everything outside of this range, like this operation is just 0. It doesn't really exist. And also that the 0th operation is just the identity. And then the final condition we have is that we have this Cartan formula, which tells us that this thing it acts basically like a graded ring homomorphism on taking cup product. Well, that's not entirely accurate. The correct statement is that if you take like the total C-node operation, which is like not really a well-defined thing, that thing is like an actual ring homomorphism in the way you want it to be. Um, okay, that's great. And now, I guess the claim here, and this you can show by like the universal coefficient theorem applied to the sequence that you use to define M, is that the cohomology of M as a module over the Steenrod algebra looks like the following. So I have just a generator in degree 0, the generator in degree 1, and then the only non-trivial operation here is a square 1. And then the claim is that the square 1 is like non-trivial. Like it sends the generator in degree 0 to the generator in degree 1. So like you can check this. It's like some computation. You can like write down an X group. It's like great. So then what does that tell you? So first, what is then the cohomology of M wedge suspend M? Well, it's going to look like the following thing. So, okay, maybe let me do this in green. It's going to look like the following thing. So we have degree 0 here, degree 1 here, degree 2 here. So our first copy of M is going to give us generators in degree 0 and 1. Our second, because we've suspended it, we'll shift it up. So we'll get to generators degrees 1 and 2. We have a square 1 here and a square 1 here. And because we just have this wedge sum, these things don't interact. We're just like taking the sum of cohomology groups as like graded groups or graded F2 vector spaces, whatever. Now what happens with H star of M smash M? Well, this thing has a basis because this is by the Kunith formula, just the same thing as A star M tensor A star M in like the appropriate graded sense. So if we let our basis of this thing be x naught, x1, then we get a basis of this thing as, and this is like going to look a bit weird, but you'll see why I choose this in just a second. So we have x naught tensor x naught, this is our degree 0 guy, of x naught tensor x1 plus x1 tensor x naught, and x1 tensor x naught. These guys are both in degree 1, and then x1 tensor x1 in degree 2. So then additively, we have generator degree 0, generator degree 1, generator degree 1, and generator degree 2. And what are the C-node operations? Well, here's like an exercise. So let this guy be x1 tensor x0, so then everything else you sort of know what it is. Square 1 of x naught tensor x naught is going to be x1 tensor x naught plus x naught tensor x1. So you have an arrow like this. Square 1 of x1 tensor x naught, well, square 1 of x1 is 0, it vanishes. Because like for degree regions, so the only non-trivial term in the Cartan formula is the square 1 of x naught, so we just get x1 tensor x1. But now we have a non-trivial square 2, where if we take square 2 of x naught tensor x naught, we get x1 tensor x1. So we have an, excuse me, I sneezed. So we have a non-trivial square 2 like this. So what we've shown is that, like, if these two spaces were to be equivalent, they would have to be, their comodules would have to be equivalent, not just as like F2 vector spaces, but as like modules over the Steenrod algebra. And like, it turns out that this isn't the case, which means that they can't be equivalent, which means that overall, M doesn't have a multiplication. And like, these sorts of like little things are like sort of all over the place, where you have like really concrete calculations you can do, and then like using this theory of power operations, you could like bootstrap it up to like much more impressive statements about like the nature of these spaces. In fact, something that I suspect a lot of you probably already know is that like, okay, like there's a functor from so like say I'm working like two locally, there's a functor from like spaces, like two local spaces or two local spectra to like F2 vector spaces, graded F2 vector spaces, which is taking cohomology. This thing naturally lifts through like graded modules over the Steenrod algebra. Um, and like obviously it's like a forgetful process. There's like you lose a lot of information just passing to cohomology, even recovering all this data with the Steenrod action. You can ask, okay, like is there a nice way to go back? There is. It's called the atom spectral sequence. Yay. Um, but yeah, that's where this story comes in. So then in the last, I guess, 5 to 10 minutes, I'm just going to tell you that basically the same sort of punchlines hold in the case of working over like EN algebras. So now let's consider the category of KN local commutative EN algebras. So these things are like the bread and butter of doing like sort of like local algebra in this like chromatic world. It's the same thing as like working over, say, like classically, this is the analog of like working over like complete um complete p local algebras, say. Now, so you have this k local commutative EN algebra. Let's call this guy T. And you can ask, okay, so what structure is on pi star of T? And the answer is that a lot. In particular, so this is largely due to Charles Resk and Matt Ando and Neil Strickland. So there's a ring, put this in air quotes, is not exactly a ring, called gamma of power operations on Kn Ian algebras. Um, and pi star of t is a it's called a graded augmented gamma ring, and that it has a like a natural structure of a gamma algebra, like up to like some sort of ideal of indeterminacy. Um, and like this ring gamma of power operations is like really computable. Like you basically know what it is, and like in sort of nice cases for like low heights where like you have explicit descriptions of these theories in terms of like say like elliptic curves, like you can just write all these operations down. Um, and sort of it's a really cool fact, and this is due to Endo, Hopkins, and Strickland, that this ring gamma sort of naturally arises from studying deformations, or really, I should say, isogenies of the Frobenius operator on some formal fixed formal group over K that like you use to cook up your E theory in the first place. So like this gamma isn't arbitrary, it has like a very natural like algebra geometric interpretation. Um, I guess the other fact I should mention here is the subject of Reszke's T algebras. So let me just say that Charles Resk constructed a monad called T, which takes in like K-local En algebras or modules over Morava E theory more generally, and it spits out a module over like like E naught, like the homotopy groups of this module. So it's a functor that goes from uh sort of like spectral algebra, higher algebra to like classical algebra. But the benefit of that is that the image of this functor is like things here are naturally like algebras over this monad T. And this thing like records all of the data of power operations of like these En algebras in like a purely like computable way. Like it turns into a linear algebra problem. Um, so like through this, I just wanted to say like one of the I think coolest like facts and lemmas that sort of shows up in this theory, which is the following like lemma slash theorem, which is that so suppose that T as before is a Kn local, maybe actually like an E infinity Kn local En algebra. So then there exist operations Q and theta on these zeroth homotopy groups of T. And these are, in particular, these are natural with respect to maps in Kn local En algebras, such that the following three conditions hold. So first is that the pth power map can be written as Q plus P times theta. Second is that Q is additive. And third is that theta of 0 is equal to 0. So those of you who have studied a bit of, I guess, like prismatic cohomology, will sort of recognize this object as a delta ring. or it's somewhat similar to a delta ring. It's not exactly a delta ring for like sort of like obvious reasons, namely that you don't require this operation Q to be multiplicative. So like this isn't really like a true like lift of Frobenius in that sort of sense. But like these operations whose existence is just like it's like something that you can like sort of construct by the fact that you like know in a precise way what like the okay, so like just as a reminder of the discussion previously, like these operations come from elements in the um the canonical zeroth En homology of the classifying space of some various symmetric groups. So like if you can compute these things, or you like sort of know how they interact with each other, you know where all these operations come from. And then you can just like sort of do these constructions. But this is a very cool theorem and it has a lot of practical applications. One of them being that this is like the sort of key technical result in the proof of the following theorem. So like this arrow here is due to Keel Matthew, Nico Noman, Justin Noel, which is that uh, so say that R is an E infinity ring spectrum, or really you can just drop this to H infinity, which is like a slightly weaker condition, or a much weaker condition, but like I won't get into the difference here. And then X is an element in pi star of R, which is in the kernel of the Hurewicz homomorphism, where here we're going to just HC cohomology. Then X is nilpotent. So this thing is often called the May-nilpotence conjecture, and it was proved back in 2015, like using like very chromatic methods, which is like sort of crazy when you consider the fact that like the classical nilpotence theorem is something that is like fundamentally a chromatic like statement. It's about like using complex Bordism to detect nilpotence on like general ring spectra. But the main nilpotence theorem is using like this sort of much more refined theory of like power operations, which is like a sort of unique feature of E infinity and H infinity ring spectrum. And what this tells you is that like these power operations, they're really powerful, but in some sense they're powerful because of how they interact with these like chromatic like structures. Okay, so I think I'll stop there. Uh, Thanks for listening. If you have any questions, I'd love to answer them.
Let's thank the speaker. So maybe I can start the recording. Ciao.